So I wanted to put down a few things that we have talked about, maybe make ourselves kind of a cheat sheet or a formula sheet, and talk about capacitors, inductors, and whatnot. So let me start this. There'll probably be quite a bit of white space here, and I'll set it aside. We'll work some problems, and then we're going to come back and put some more on this. So let's say that we've got a capacitor. Our equations, our governing equations for the capacitor is that I in the t domain is equal to the value of the capacitance C times dV dt. And then if we want the voltage across the capacitor in the time domain, that's 1 over C times the integral of I of t plus then the initial charge V t naught. Okay. And we could do similarly for an inductor. We've got that the voltage across the inductor then, remember the inductor and capacitor were the same but kind of opposite. The voltage across the inductor is L times di dt, and then the current through the inductor, I of t, would be equal to 1 over L times the integral of V dt plus I t naught. Okay, so as we work through our problems and whatnot, we'll come up with an equation. These then are what we're always trying to get rid of when we use the Laplace transform. I'm just going to leave this white space here. We'll come back to page number 1 and add some more things to it later. So I'll set that off to the side. What I'd like to do then is go back and look at the problem that we finished up with last time. I think this is also a homework problem, so I don't want to wear this problem out, but I think there's probably some value in taking a problem and doing it a lot of different ways and getting some confidence in this when we know what the answer is so that we can make sure that we're getting it right. And we will definitely in lectures to come talk about different problems and certainly more difficult problems. So if you go back and you look at that problem, we had a 12-volt source. Like I said, I think this is one of your homework problems too. So you'll have to get down one more time. So at t equals 0, we open this switch. We have a capacitor here. We got a 4K resistor and a 2K resistor. I believe this was a 100 microfarads, and this was what, 3K? And we were looking for the voltage across this. We could say V naught at t. So that's what we were looking for. And as we were talking last time, we went through the 6-step method, and I will just hit the really high points in this. And we're not. This will probably be one of the last times we talk about or do the 6-step method. I just use this as a way of coming up with the answers and comparing it to that. With the 6-step method, we found that the voltage across the capacitor you would open that capacitor up. You'd ask the question, what's the voltage across there? So voltage across the capacitor. And we said that the voltage across the capacitor then at t equals 0 minus was by simple voltage division equal to what? 12 times 6 over 9, which is 8 volts, right? And this also will in a lot of our problems, when we go through this using the Laplace transform, we'll still have to do this. So this is something that's pretty important to be able to do. The other thing is, I think when I was finishing up last time, I think I said that that was 0 plus. If I go back and look at that slide, this is in the PDFs. I actually corrected it in the PDFs before I posted them. But when I lectured on that, I actually put a plus sign there. It should be 0 minus. It's before the switch is thrown, right? So as you're watching those videos or in your own notes that you've taken, make sure that that is a minus and not a plus, because it's before the switch is thrown. So we've got that, and then we go ahead and we throw the switch, right? And when we throw the switch, we can come up with this. We're going to put the voltage here for what we had in the capacitor. We've got 2K and 4K, and so we then ask the question, what's the voltage across here? V0 at t equals 0, which we can just do by voltage division, right? 8 times 2K over 6K gives me 2.667 volts. Okay, so I mean, if we're keeping track of this, this is t equals 0 minus. This is t is equal to 0 plus. And now we need to look at t equals infinity. It goes to steady state. What's that going to look like? Let's see, a capacitor is going to look, this is going to be open, isn't it? There we go. So we got something like that, and we ask, what's the voltage across this at t equals infinity? That's 0. And then one of the things that we wanted to do is we wanted to look back into those terminals. And look at the equivalent resistance here when this is 2K and 4K. And we get then that the equivalent resistance was equal to 6K, which is equal to the Thevenin. So we can say then that the time constant is equal to that R Thevenin, 6K, times the capacitance, which is 100 micro. So you have 6 times 10 to the 3 times 100 times 10 to the minus 6, which gives you what, 0.6 I think is what we had. So you can pull this whole thing together, this piece of information, this piece of information, that piece of information. I'll see if I can get this on one page here. And you'll say that you have then, get a little space here. That our voltage V0 t is equal to 0 plus 2.667 e to the minus t over the time constant, which is 0.6. If I tidy that up a little bit, get rid of that 0, we have 2.667 e, and then invert that 0.6, and I have minus 1.67 t, and that would be volts. And I think that's what we got last time. And like I said, I'm not going to belabor this. This will probably be the last time we go through it. It's kind of nice to have a problem that we have an answer to. So when we try it with a different method, if we get the same answer, we'll get some confidence. If we don't get the same answer, we're going to have to go back and try and justify that. That also gave me a chance to talk about the lecture notes and make sure that that was corrected. So let's set this aside, except for the answer. So we'll remember we have the answer there, and see if we can do this with Laplace Transform. I think we did it last time. I'm going to do it a couple different ways as we go through this. No, I'm going to use the same circuit. So I'm going to start with this. I'll repeat it here. 12 volts. So again, we're looking for this. The one thing that you have to do is you have to say that the voltage across that capacitor at t equals 0 minus is equal to 8 volts. Okay, so you can go back to, so even though we're probably not going to do the 6-step method again, we're going to end up having to do the first part of the 6-step method many times because we're going to come up with the initial voltage across that capacitor or the initial current through the inductor. So we've got to have this piece. And then I look at throwing the switch, and when we throw the switch, we've got this capacitor in here. And the 4K ohm resistor and the 2K ohm resistor. And I have something like this. And I think as I go through this, I'm going to do it a couple different ways, but I'm going to look initially at this current going like this. So I'm going to say that this is I of t. We'll come back and do it with the current going the other way. So if I look at that, this would be a positive and negative, and positive and negative, and then positive and negative. So I have to be careful with the voltage of potential of V0, but I think I can get through that. I'll say that this is Vc of t. This was the 2K, and this was the 4K. So if I use then Kirchhoff's voltage law on this thing, what do we come up with? I would have, if I went around here, I'd go from positive to minus, so that would be a drop. So I'll just go ahead and take drops as positive. Vc of t plus, then I've got a drop there and a drop there, so 2 and 4 gives me 6. So I have 6K I of t. Those are both drops. We'll set those equal to 0. So I take that expression. I've got a bit of a problem there because I have V sub c and I have I, two unknowns in that, so I need to make a substitution. So I'll come up here and I'll say that I'm going to note that I of t, what's that? We have our cheat sheet. Going back to page number 1 with our cheat sheet for yeah, c dv dt, right? So I've got c dv sub c of t dt. Okay. So I'm going to make that substitution for I of t. So I now have v sub c of t, then plus 6k, and then c, that's 100 microfarads. And then I have dv sub c of t dt is equal to 0. So let's see, this is 6 times 10 to the 3, 100 times 10 to the minus 6. Make sure you use your base units on that. When you get done with that, what does that turn out to be? I believe that's 0.6. So we have then Vc of t plus 0.6 dVc of t dt is equal to 0. Let's see, those of you in Math 256, that's what? First order homogeneous differential equation. I mean, that's why this comes up, why oftentimes in math you'll be talking about Laplace transforms, because it's a great way to solve equations like this, differential equations. This one comes from electrical. You may have them that originate from other disciplines. So I'm going to take the Laplace transform of this then. So taking the Laplace transform of this, what do I come up with? The Laplace transform of this piece is what? That's just Vc in the S domain, isn't it? And then how do I take the Laplace transform of the constant? I'll just have then the constant times that. And what's the Laplace transform of a derivative? That's that one where I have S times Vc in the S domain, and then I have to subtract off the initial value, right? Okay, is equal to 0. So I've taken the Laplace transform. So I could say that I have Vc in the S domain plus 0.6 SVC in the S domain is equal to, I'm going to put, do we have this? This is 8, isn't it? Okay, so if I put an 8 in there and I observe this negative sign and multiply it by 0.6, I end up with what? Minus 4.8. And I move it to the other side, so I will have positive 4.8. So positive 4.8. So I factor out a VC in the S domain, and that's going to be what? 1 plus 0.6 S. So I can then solve for VC in the S domain. I'll use consistent script here. VC in the S domain is equal to 4.8 divided by 1 plus 0.6 S. Okay. And I'd like to make that a little more convenient to look at, so I think what I'm going to do is I'm going to multiply this thing by 1 over 0.6 top and bottom. So multiplying the top by 1 over 0.6 and multiplying the bottom by 1 over 0.6. So when I do that,
the point of that is to get S by itself.
yeah, so it looks like something we've seen before, hopefully. So I come up with VC in the S domain is equal to, I'm back to 8, aren't I? 8 in the numerator, and then S, I think I'll change the order to, and 1 divided by 0.6 gives me what, 1.67? Okay. So hopefully we've seen something like that before. That looks like that's in great form to do the inverse Laplace transform, doesn't it? So let me do that. Take the inverse Laplace transform of that, and we will end up with, back in the time domain, so VC in the time domain is equal to 8e to the minus 1.67 t, and I've got that u of t trailing along, indicating that that starts when the switch is opened or closed or moved to the new position. Now I don't think we were looking for v sub c. We found v sub c here. But I mean, if I found this as v sub c across here, could I get this? Should be by simple voltage division, right? Okay, so I can say then that v naught of t is equal to vc of t times what's that going to be with the voltage division? 2k over 6k. So that gives me 2.67 e to the minus 1.67 t u of t, which I think that's what we've seen before, haven't we? I'll go back to the 6-step method here. There is our answer for the 6-step method. It didn't have the u of t, but we understood the switch. That was after the switch was thrown. So I think we're okay with that. So I'd like to take that. I think we should have some confidence in that method and maybe try it a little different way. Okay, this one I have the current going maybe what I would like to think is the wrong way. So maybe I'd like to do it with the current a different way, and maybe I'd like to tackle it by solving the current. I mean, we had an option here. We could have substituted in for the current and solved for the voltage. We could have substituted in for the voltage and solved for the current. So let's try that. So I'm going to come back over here. I'll use a little space here and redraw this thing. So I'm just going to back up to the point where the switch is already thrown. We've got 2k here and 4k here and VC of t. And I think this time I'm going to go ahead and put the current in probably a little more comfortable position for me. I tend to like it in the clockwise direction. So I of t, and this is still 100 microfarad. So I think if I start here and work my way around the circuit, just like we've done before using mesh analysis or Kirchhoff's voltage law, let's see what we've got. What's the governing equation for going back and looking at my cheat sheet? What do I have for the equation for a capacitor? I could talk about the voltage being this thing right there, right? So I've got 1 over C times the integral of I of t plus the voltage across the capacitor at T naught. Everyone's okay with that? So that's that piece. And then as I go around, I've got a drop across those. So I can combine the 2 and the 4. That's obviously 6. So I'll just say that this is 6k times I of t. Gets me back to my starting point. I can say that's equal to 0. Okay. So now I've got it all in terms of current except for this one. Let me go ahead and substitute some values in here. When I have 1 divided by 100 times 10 to the minus 6, I get 10,000 in the numerator. That'll be the integral of I of t dt. I forgot a dt there. And then this one is the tricky one here. I have to be careful with this. This initial voltage is really sitting in here like this, isn't it? And we found that, what was the polarity on that? If we looked back on that, when we solved for that way back here, when I solved for this 8 volts, that was assuming it was positive there and negative there, right? So if I look at that polarity, I have positive and negative. So everything I was taking as a drop, but that's a gain, isn't it? So I better indicate that, minus 8. And that negative comes from it is a gain. And then I've got plus 6k I of t is equal to 0. So I go through some math there. This turns out to be 10,000 times the integral I of t dt plus 6,000 I of t is equal to, I'll move that negative 8 to the other side, and I have a positive 8, right? Okay, so we're doing the same problem. I assume my current differently. That should not concern us. I mean, we've done that. It's assuming current one way or the other since fall term. I'm solving now for the current. So I'm going to have to do a little manipulation once I get this current, because I'm still going to eventually find this voltage here. Okay, but we should be able to do this. So I think I'm ready to take the Laplace transform of this, aren't I? I should be. So I got a constant here that's 10,000. And then integration, that's the real bargain in this business, isn't it? That's just division. So I'm going to have I in the S domain divided by S. And incidentally, I am taking the Laplace transform right in here. And then I'm going to have what? Another constant, multiplication by a constant. And then I just transform this I in the T domain to I in the S domain. And how do I handle this 8? 8 over S, isn't it? Yeah. So I can start to rearrange this now. If I solve for I of S, I have what? 10,000 over S plus 6,000 is equal to 8 over S. So I can say that I in the S domain is equal to 8 over S divided by 10,000 over S plus 6,000. And I mean, theoretically at that point we'd take the inverse Laplace transform. I think I'm going to tidy it up a little bit before I do that, make it something that's hopefully a little easier to recognize. So I'm going to multiply numerator by S over 6,000 and denominator by S over 6,000. So there we go again, multiplying by an odd looking 1. So when we do that, we've got this over here, and we could say that I, still in the S domain, we're just changing the looks of this a little bit. We're going to cancel those S's and divide 8 by 6,000, so I get a small number, 0.00133. And then what do I have here? I cancel that S, and so I have 10,000 over 6,000, 1.67, plus I'm left with an S. That looks vaguely familiar, doesn't it? So with that, then, I will take the inverse Laplace transform. Taking the inverse Laplace transform, I come up with then I in the t domain is equal to 0.00133. You could probably get a little bigger number if you use milliamps, but I'll stick with base unit of amps and leave it like that for a while. E to the minus 1.67 t, and then I have that u of t, right? And that's not what I'm looking for. I'm really looking for v naught. Well, what's v naught? That would be equal to 2k times I of t, wouldn't it? We saw that weeks and weeks ago, months ago. Seems like almost a lifetime ago at times. But v naught t would be equal to, I mean, if you think about what you've learned in the last 8-9 months, it's incredible, right? Yeah, so v naught t is equal to I of t times 2k. So that gets us to multiply this number here by 2k, and you come up with 2.67 e to the minus 1.67 t u of t. So again, we take the same problem, we get the same answer. We're starting to get some confidence in these methods, that there's not just one particular path. There's a lot of wrong paths that we have to be careful of, but there are a lot of right ways to do this too. Well, let me... it's kind of interesting that a lot of times we come up with something that looks like this. You see that? In the S domain. And then when we did it the other way, did we have something, yeah, right here, a little bit different, but again, it was in the S domain. So it'd be kind of interesting if we could just go and represent that circuit and write the circuit in the S domain. Okay? So let's try that. So what I'm going to do before I do that is I'm going to run back to my formula sheet and I'm going to add some to this. So that was my page 1 here. I'm going to jump back to that and add some information here. And this is very much like table 13.1 in your textbook. Okay, I'm going to use slightly different symbols and whatnot, but the same basic thing. So what I want to do is I want to talk about if I have something in the time domain, what that looks like in the S domain. And the first thing, the easiest one, is the resistor. That's very easy. So I could look at this resistor and talk about I of t and the resistance, and then the voltage across here, V of t. And if you go into the S domain, there's not much difference. Pretty easy. So we've got the resistor, then we'll have I in the S domain, and we'll have V in the S domain. Okay. So our resistors we're going to treat pretty much the same, whether we're in the S domain or the T domain. The plot, of course, thickens with capacitors and inductors. So again, I'm just summarizing table 13.1 in your textbook. But let's say if I start with a capacitor that looks like this, and I'm in the T domain, so I have V of t, and I've got the current here, I of t. I have some capacitance. I could say that this was in the S domain, would look something like this. It's going to be a capacitor, and then I have to deal with that initial charge on that thing, so I'll deal with that in terms of a voltage source. Okay. So I'm going to say across here is then V in the S domain. This capacitor takes on the value of 1 over SC, Okay, because remember we're representing this in the S domain now, not the time domain. And if we look at this voltage source, this is the initial voltage, V at t equals 0, divided by S. Okay. And I could say, if I wanted to, then that this Vs, I could just sum this up, is equal to, I need the, better put this current here, I'll say this is I of S. So I could say that I have the voltage is I in the S domain divided by SC, that accounts for the capacitor, and then I have V naught over S for the initial voltage there. Double check that, yeah, I think we're okay. Now we could also, in some cases, and we're not going to get into this today, but we may want to look at this instead of a voltage source in series, a current source in parallel. So let's try that, see what that looks like. So we'll take our capacitor, and we're going to have again some voltage Vs across this, and this capacitor is going to be 1 over S times C. And I'm going to, across this thing, I'm going to put a current source. And that current source will have the value of the capacitance C times the initial voltage. Okay. And we would still have the current then, IS. And if I want to talk about IS in this case, we could say that that's equal to S times the value of the capacitance times V of S minus C times the original initial voltage. I'll double check that. Okay, so I think I'm going to try and squeeze the inductor in here so we can just get it all on one page. It's going to be a little bit tight, but I'll do that. So the inductor in the time domain, and this may be a little bit confusing, but we're going to put this into play real soon. We're going to go back and do that problem that we've done many times, and we're going to go right to writing the equation in the S domain. So there's our inductor in the time domain. So we could talk about I of t and V of t, and this has some value L. And we could represent this in the S domain. We could represent it very similar to the capacitor. We could represent it as an inductor in the S domain in series with a voltage source. So we'll put Vs across here, V in the S domain. This will be I in the S domain. And this will take on the value S times the inductance L, and this has a polarity that's negative at the top, positive on the bottom, and it's going to have a value of L times whatever the initial current was. Or we could represent this as the inductor with a current source in parallel. So again, we have S times L. Here's I of S, V of S, and I'm going to put this current source out here. And looking at the polarity of the voltage source, the current source would have to go down. This is going to be the initial current divided by S. And if I wanted to talk about the V of S here, I could say that that's going to be equal to S times L times I in the S domain minus, because of the polarity there, L times the initial current. Or if I wanted to talk about I of S in this case, I would say that it's Vs divided by SL plus I naught, or the original current, divided by S. I'm going to double check these, make sure we got these right, because we're going to use these on a lot of problems. I think we're okay. Okay, so that may be more confusing, but I think once you get used to this, some of you will probably like this. I tend to like just writing it in the time domain and doing the Laplace transform, but if you're going to go into this as your business, you probably want to be able to go directly to writing it in the S domain. So let's go back to that problem. Yes?
On your second diagram on the bottom, L times I naught, that's a power supply?
Yeah, it's a voltage source, yes.
With the opposite polarity of the events.
Yes, the voltage source is sitting in there like that. Okay. Other questions? And again, if you want to see this in maybe a little better font and whatnot, they use slightly different symbols than I use, but your author, table 13.1, is a good reference. So let's try this thing. We're going to go back to this circuit right here. So again, I'll redraw something like that. We've looked at that many times. Let's go look at it one more time. So where were we here? We're at 5. So I'm going to start out with the capacitor. We had a resistor, and that's what we had. This was 4K. This was the 2K. This is what we were looking for, the voltage across there. That's what we were trying to find. This was that 100 microfarads. This is the time domain, right? Okay. So I want to show what this thing looks like in the S domain. So I come over here, and I think I will try and represent it this way. Okay. So I'm going to do it in the S domain now. So I'm going to put that capacitor there, and I'm going to put it in series with a voltage source, like this. Okay? And I'm going to say across here is Vs. Okay. And then this capacitor is going to look like what? 1S over C, and this voltage source, the initial voltage over S. So far so good? Now to do that, the current's got to be going which way? It's going down through this thing, isn't it? So the current's got to be going like that. So I'm going to have to represent the current going there. I'll say that this is I of S. Okay. Now I put the rest of the circuit in here. Resistors, those are pretty easy, right? Okay. 2K. 4K. Are we good on that? So there's what the circuit looks like in the S domain. And I was using this one right here from our cheat sheet. So then if I want to talk about Vs, if I use Kirchhoff's voltage law, I can go around here Vs. So what's Vs equal to? We see it right here. Yeah, I of S over S times C plus the initial voltage over S. This is Vs. Try and be real clear on this. I won't always do this, but as we're going through it the first time. So that's essentially a drop. I mean, if I start there and go the direction of current, that's a drop, then I would have a drop across this and a drop across that. So I could just say that 2 and 4 course is 6. So I will add this, looking at drops, 6K IS is equal to 0. We good with that? Okay, so let's start to put the values in here. We've got essentially 1 over C times IS over S plus V naught over S, or the initial voltage, over S plus 6K. I didn't make much progress with this step, did I? This one is what? When you look at this value here, you invert the 100 times 10 to the minus 6, and this turns out to be 10,000, doesn't it? Okay. And what is this thing? Did we have that value?
8.
Yeah, that was 8, wasn't it? We've used that many times before. That was the initial voltage across the capacitor. So good. With that, I can say that we have I in the S domain times what? 10,000 divided by S plus 6,000, because that's got an IS. And then when we move this 8 over S to the other side, it became what? Minus 8 over S. And I think we did an example where we had one that was a positive 8 over S, but I was using a different direction on my current. So I think we're probably still okay. So you see, I converted the circuit from the time domain instead of writing my equations in the time domain and converting it. I mean, I've already taken the Laplace transform. The Laplace transform was taken when I wrote this circuit. Okay.
So if we started from scratch, we wouldn't know that V naught or V to get it.
Right, you'd still have to go back and get that. Yeah, you have to have this. Okay. So let's see, I could solve this for I of S, right? Is equal to minus 8 over S divided by 10,000 over S plus 6,000. What do we want to multiply by? Yeah, S over 6,000 here, S over 6,000 there. So I come up with minus 0.0013 divided by 1.667 plus S, right? And I say, hey, this has a negative sign in it. The last time we did this dealing with the current, we didn't have a negative sign, did we? Where was that? Well, that was this one here, wasn't it? But which direction was this current going? That was going clockwise. Which direction is our current on this one going? Counterclockwise. So we would expect that difference. Okay, so we go through this. Time to do the inverse Laplace transform now. We've taken pretty easy functions, haven't had to do the partial fractions. That will be coming. We'll work some more difficult ones in here soon. So in the time domain, we have minus 0.0013 e to the minus 1.67 t, right? And then u of t. Is that the same thing that we've got in the past? It better be. Yep.
When we transfer back to the time domain, that negative 1.67 from the denominator. Is that what happens if that is negative 1.667 plus S in the denominator? The exponent positive.
Yeah. So we weren't looking for the current, we were looking for this voltage across here. So we recognize if the current is going up, right, we would say that this voltage in the time domain would be equal to, if this is I in the time domain, it would have to be minus I in the time domain, wouldn't it? Should probably have that as lowercase times 2k. So I say then that V of t is equal to minus 2k or 2000 times I of t, which gets me the positive 2.67 e to the minus 1.67 t u of t. That would be volts. Okay. So we probably beat on that problem about as much as you want to. It's a homework problem, like I say, so you got a variety of different ways that you can choose to document that in your homework. But I wanted to go through this problem first, finding what the answer was, and then starting to play with it and seeing how many different ways I could do it. There's probably still many other different ways that I could do it, but I think this is good practice. Okay. Let's move on to another problem, unless there's questions. A little more difficult. And it's one that I definitely want to do. That I think your last homework problem, it doesn't have the solutions. It says to see class lecture for the solution. So I guess I had better do a class lecture for the solutions. So I think that problem is D4 in your homework problems, and looks like this. 12 volts there. The switch is thrown open at t equals 0. We got 4 ohms here, 2 henries there. And we got another 12 volt source here, 2 ohms. And this is not very realistic, but hopefully it keeps our math easy. 1 farad. So we'll do something like that. Okay. And no, we'll do something. We need this 4 ohms in here. I better make sure this is the same problem. Yeah, I think we're good now. So what are we looking for here? We're looking for I of t. So we'd like to find the current through that cap. Okay, what that's going to be. This one, I mean, the previous problem, we started out using the 6-step method to get an answer so we could check our work as we were going along. We couldn't use our 6-step method on this because there's 2 energy storage elements, an inductor and a capacitor. There is a chapter, I think about 7 or 8 in the textbook that talks about how to do that with an RCL circuit, but I think we've got a good tool here, so let's just use it. The first thing that we're going to have to do on this is we're going to have to look at those initial conditions. So we'll say for t less than 0, or maybe you would write it as t at time equals time is equal to 0 minus. Okay, so the switch is still closed. What's this thing going to look like? Well, what do inductors look like to a circuit that's been sitting for a while? Yeah, or a short, because our inductor has 0 resistance, right? Yeah, so we got a wire here. We've got that in there. The switch has been closed for so long we don't even know it's a switch. So we're going to come up with this I sub L, okay, at t equals 0. Put this voltage source in here, 4 ohms. And what do capacitors look like when they've been sitting for a long time? Open, is that right? Okay, so we're going to ask the question, what is V sub C? And we're going to ask the question, what's the current I sub L? So let's see, I sub L, I don't think these are too difficult. This current through, that would be the same as I sub L, wouldn't it? This current here? which is that current there. So effectively, it's the current through that 4 ohm resistor. And what's the voltage across the 4 ohm resistor? Well, because this is open, really the voltage across the 4 ohm resistor is 12 volts, isn't it? So I could say that I sub L is equal to 12 volts. I mean, that only works when this is open. If this was closed, it'd be a whole different game. But because this is open, I just have 12 volts across there. I got 12 volts. I got 4 ohms. So I've got 3 amps. And it's important to note the direction of that. It is going down. Okay, so this is I of L at t equals 0 minus. I wanted to be very specific. Let's see, V sub C. Well, what's the current through this 2 ohm resistor? Should be 0. How about through the 4 ohm resistor? 0. Okay, great. So now what's the voltage from, let's say, there to there? Well, let's see. I start here, I gain 12, and I gain another 12. Be 24, isn't it? Yeah, I have 12. I gain 12 here, and I gain another 12 there. I don't drop any across the resistors because there's 0 current, so I have 24 volts. So I could say voltage across the capacitor at t equals 0 minus is equal to 24 volts. And again, the polarity is positive here and negative there. We want to definitely hang on to that. Okay, so no matter how you do this, whether you're going to write it in the time domain or whether you're going to write it in the S domain, you got to have a handle on these parameters. And probably most important is the polarity of them. So this is very important. Okay. Well, let's go ahead and write this thing in the time domain. Okay, so what's this thing look like in the time domain? Once we've thrown the switch, we open up the switch and we just have this voltage source hanging out here, not doing any good. So I'm left with a inductor, a resistor, and then I'm going to have this voltage source here, another resistor, a cap, another resistor, and this thing just comes around, right?
So this would be time equals 0 plus.
This is time equals 0 plus, yes. Yes, thanks. Good point. So we got 2 ohms here, 4 ohms, 2 henries, and 4 ohms. Everyone's okay with that? I like currents clockwise, so I'm just going to go ahead and assume I of t that direction. And I'm going to write my Kirchhoff's voltage law. Very similar to what we would have done with a DC problem. But we'll have some terms that wouldn't have cropped up with a DC. So if I start right here and start working my way through this inductor, we go to our note sheet here. What do we know about inductors? What's the voltage through an inductor? L di dt, right? So I've got L di dt plus, we've got this resistor. I think we're probably all at the point where we don't need to write 4 times I of t plus 2 times I of t plus 4 I of t. Let's just take that as one fell swoop. 4, 2, and 4 gives me 10 I of t. Good with that? Okay, keep this a little more manageable. So I've taken care of the resistors. I've taken care of the inductor. As we move around this thing, we've gone through this voltage source. We've taken drops as positive. This voltage source is a gain. I'm going from negative to positive. So how's that going to show up? Negative 12. So our drop is positive, like we've done many times in the past. So that's a gain. So that's going to show up as minus 12. I've got all the resistors. I just have to deal with the capacitor. What does a capacitor look like? Yeah, right there. This one. Okay. So 1 over C. What's that?
The capacitor, where's the dt for it? Is it right after the I?
Oh, yeah, I guess we should put a dt there. Okay, yeah. Wouldn't get very far without that. We okay then? Yeah, that should be a drop. So I can just say that it's plus 1 over c times the integral of I of t dt. And then I got to take into account that initial. So plus v c at t naught. And that is equal to 0. That gets me back to my starting point, right? So I got a little tight on space there, but I think we can get through this. So let's see, what do I have to deal with? I got L, what's that? That's 2, isn't it? 2 henries. C, that's 1, isn't it? So that'll make that kind of nice. This one, what's this? Yeah, it's 24. That was a drop, wasn't it? So I should be good. So I have then 2 times di of t dt plus 10 I of t plus, because 1 over 1, because c is 1, so I just have then the integral of I of t dt. And I have 24 here. When I move it to the other side, I got negative 24. I have a minus 12. I move it to the other side, I get positive 12. So what am I left with on the right-hand side? Negative 12? Yeah. Okay. Because this minus 24 goes over as negative. That negative 12 goes over as positive. So I'm left with minus 12. So I'm ready to tackle this thing. I need to, take the Laplace transform of it, right? So let's do that. So I'm taking the Laplace transform of this. What's that going to look like? A constant, 2 times, and then the derivative, that's s I in the s domain minus the initial current. Plus 10 I of t, that's easy, 10 I in the s domain. And then what do we have? The integral, that was the real bargain, right? Plus I of s divided by s, that would have been nice in what, Math 252, right? Is equal to minus 12 over s. There's our step function. So I think we're good there. Let's make the substitution for this. So this we have to be pretty careful of. So we go back and we look at that initial current. What was that initial current? It was 3 amps going down, right? So when I get over here, I'm talking about the current going up. So what should I substitute in there? Negative 3. And the negative becomes from the direction. So I'll have this negative out here that's by virtue of the Laplace transform, and I have this negative here because my current is going in the opposite direction of that initial current. That is to say that we found this initial current going down. We are now analyzing this, though, with this current going up. So I got that negative 3. So we end up with 2s I of s plus 6 plus 10 I of s plus I of s over s is equal to minus 12 over s. So factor out an I of s in here, and we have what? 2s plus 10 plus 1 over s. is equal to minus 12 over S. So I of S is equal to, yeah, so this should be minus 6, shouldn't it? No, I left that off. Good. Okay, so now we have minus 12 over S minus 6 divided by 2S plus 10 plus 1 over S, right? So I think what I'll do is S over 2, yeah. So we end up then with minus, what, is that right? Let's see, so I multiply by S, I cancel that out, negative 6, okay. So minus 6 minus a 3S, okay. And then here I've got S squared plus 10S over 2, which is what, 5S? 5S, and then plus a half. So I think I'll change this, clean this up just a little bit more. I want to get my orders correct here. Minus 3S minus 6 divided by S squared plus 5S plus a half. So we're at that point, we're ready to take the inverse Laplace transform, right? Well, we're going to have to use partial fractions. We've got some more work to do on this one. But I think what I would like to do is hold off on that a little bit and go back and look at the circuit in the S domain. Okay? So, and hopefully when we do the circuit in the S domain, we will come up with the same expression, and then whether we've done it in the S domain or the time domain, we'll do the same inverse Laplace transform. So let me start to set this up. I don't know that I will finish it, but in the time domain we had something like this, right? So let's see what that looks like in the S domain. So, but in the S domain, so what's this thing going to look like in the S domain? I kind of like analyzing it as a loop, so I think I will use an inductor that is in series with a voltage source. So I'll have this inductor here, and I'll have this voltage source. And of course the resistor, that's easy. The voltage source, that I have to be a little careful with. Resistors again, easy, 2 ohms, 4 ohms. Then the capacitor, and again I think I'll take the capacitor. It would be kind of silly to put it in parallel with a current source. I like being able to just do one loop on this, so this is probably a smart move for us to put it in series with a voltage source. And we've got the resistor. We can put this all together. So the resistors were easy. We've got those done. This inductor, what does an inductor look like? We'll go back to our cheat sheet here. Yeah, SL, right? So I've got SL. And then what's the voltage source? We're told that voltage source is going to be, yeah, but I'd like my current to go like this. Can I make that happen? Now let's see. Look at that. Okay, so what am I going to call this? L times I naught. I think I'm good there, and that would then be what? Positive and negative? Okay, so we've got that. Then my capacitor. How do I handle the capacitor? 1 over SC. That's got that taken care of. And then the voltage source. My current's going in the right direction. It's going that way, so this will just be positive and negative. And V naught over S, right? I think we're good there. Now the last thing is this voltage source. What did that look like? It didn't look like 12 anymore. It was 12 over S, wasn't it? Okay, when I go into the S domain. So, again, I will start here and I will do Kirchhoff's voltage law, going around this thing in the clockwise direction. So what are we going to have? This is a gain, so minus L times I naught, or the initial current, I should say. Then plus, this should be a drop, S times L times I in the S domain. And then we have a drop, so another positive, and I'm just going to lump all the resistors together again, 10 IS. And then this is a gain. So this was a gain, that's a gain, so this will be minus 12 over S. And then I get over here, what am I going to have with the capacitor? Positive IS divided by SC. You multiply that by IS, you can get that. And then this was a drop, wasn't it? So I can just say it's positive initial voltage over S. Gets me back to my starting point because I've included that 4 ohm resistor in that 10. We should be good there, right? So let's see. The initial current, it was opposing this, wasn't it? My current is going this way. The initial current that we found in that inductor was going down, so this is still a minus 3. So I have minus, the value of the inductor is 2 times a minus 3 because of the direction of the currents, plus S times the value of the inductor is 2, plus 10 minus 12 over S plus IS over S, because C is 1, right? That was 1. This is 2. And then what was our initial voltage? That was 24, and it had the same polarity, didn't it? So I just say 24 over S is equal to 0. Well, I think we're getting fairly close. What's this going to look like? I'll have 2S IS plus 10 IS plus IS over S is equal to, I move those over, I have minus 24 over S plus 12 over S. So yeah, let's keep at it. We've got a couple more steps here before we call it. Can I add the 6 for the inductor? Oh yeah. I keep forgetting that, don't I? Yeah. That would be a positive 6 there, wouldn't it? So it's going to end up here as a minus 6. Thank you. I'd have had a mess there, wouldn't I? Yeah, we're good now. So if I keep going on this, we've got IS, let's see, 2S plus 10, is that right? Yeah, plus 1 over S is equal to, see, minus 24 plus 12, I get minus 12 over S minus 6. I think we've seen this before, haven't we? Let's see, minus 12 over s minus 6. I got 1 over s, 10. Yeah, exactly the same.
What about that negative 24?
Minus 24 over s. The one we're working on? Yeah, I had this that these two combined because they have the same denominator. Okay, so for completeness sake, we'll finish this up as I of s is equal to minus 12 over s minus 6 divided by 2s plus 10 plus 1 over s. And again, we're going to multiply by s over 2. Oh, come on. S over 2 and s over 2. So we come up then with minus 6 minus 3s divided by s squared plus 5s plus a half. So we get the changing this just a little bit, rearranging the order of the numerator, or 3s minus 6 and s squared plus 5s plus a half. And again, we are ready to take the inverse Laplace transform. And I think that we're dead on with this guy here, aren't we? Yeah. So the good thing is, whether we write it in the time domain, so there's the S domain, or whether we write it in the time domain, we get to the same answer. We're going to have to do the same work with the inverse Laplace transform. We're not done on this thing yet. Brush up your partial fractions over the weekend. We'll come back and tackle that with partial fractions. I tend to like to write it in the time domain, but then I'm a mechanical engineer. I think those of you going into electrical definitely want to master the S domain, even if you're probably more comfortable in the time domain, because it's just a whole lot faster. Well, that's where we'll go. We'll come back and we'll pick up at this point right here. We'll do the inverse Laplace transform on those and see if we can come up with the solution. So take care till then.